So let's take a look at what the Ka expression would look like for the dissociation of hydrochloric acid. So I'm going to write out what the equation is first, where I've got my HCl, and I'm going to add that to some water. Now I know at this point that hydrochloric acid is the strong acid in this case, and I want you to notice how I'm writing this arrow. So notice that I've got this arrow that I made fairly long on the top, and I'm going to make this little tiny arrow on the bottom that is a much shorter. This is how we indicate that equilibrium is going to lie to the right. And we still put that little tiny arrow in there because there's always going to be one particle that doesn't dissociate. So, just like we've learned before with our dissociation reactions, I'm going to have the hydrogen donate itself to the water, and I'm going to end up with my hydronium, and that's going to have an extra proton with plus charge, and I'm going to have my conjugate base with my minus charge. So now I'm going to write the Ka expression, and the only reason I'm rewriting this out is, first of all, to tell you that I can have an A down here to represent that I've got an acid, even though I'm still dealing with concentrations here. And it would be the concentration of hydronium, and I put the little plus there, concentration of chlorine, I put the little minus inside or out, it doesn't matter, and then I've got HCl on the bottom here. Note I am not putting in water, and I'm not putting in water because water is a solvent in this case, and it's a pure substance, so it has no concentration. And so it's the solvent doing the dissolving, so it does not take place or does not have a place in the Ka expression. And now we're just going to write a literature value down. The literature value just comes from a table that you will find in the IB booklet. And the IB booklet is in your red folder on the materials page in Schoology. But a lot of these problems I'm going to give you the Ka value. And scientists have proved time and time again that the Ka value for the dissociation of hydrochloric acid is 1.3 times 10 to the 6th. And notice here that the units will be moles per cubic decimeter or moles per liter. And that's because I will be left with 1 mole per liter here when I cancel out 2 of the concentrations units. So, incredibly strong acid here. That's going to say that 1,300,000 particles of HCl are going to be dissociated into hydronium and chlorine. If I have a value that is so much greater than 1, I know for a fact it's a very, very strong acid. Let's look at the example of a weak acid. Here's my ethanoic acid, otherwise known in America as acetic acid. And we dissolve 3% of that in water, we get vinegar. So let's write out the dissociation equation again. Never hurts to see that. Notice that when I have a weak acid, a lot of times you're going to see that hydrogen at the very end. And that's an indication that you've got a weak acid because it's an organic acid. So this is the reason why we write the hydrogen at the end on this particular acid. It's because it's organic. And then it's going to dissociate in water. Water again is my solvent. Watch my arrows. I'm going to have a long arrow going to the left and a very short arrow going to the right. And that's going to indicate that I'm going to have more reactants left over than products because hardly any of this ethanoic acid is going to dissociate. So I will end up having the hydrogen donate itself to the water, and I am again going to make some amount of hydronium, although not a lot, and I'm going to end up with my conjugate base being CH3COO with a minus charge. My Ka, I can write it out just like before. I'm going to have concentration of H3O plus, concentration of my conjugate base, my CH3COO minus, all over the concentration of my ethanoic acid. Don't have to write water again because water is the solvent in a pure substance. And through countless experiments over time, scientists have come to accept a literature value for the Ka value for ethanoic acid as 1.8 times 10 to the negative fifth. And again, my units are going to be moles per liter or moles per cubic decimeter. And notice how much smaller this is than 1. This indicates that I will end up with a lot more ethanoic acid still in my solution than I will hydronium. So equilibrium will definitely lie to the left. And so that's how I would symbolize the Ka values for a strong and a weak acid.